Okay, morning, and we are all ready to go. If there are any issues with my audio or anything on my screen, please type it in the chat. So the way I've set it up is I've got my iPad open here on my left, and I'll keep glancing at the chat from time to time. So if you have any questions, feel free to ask them there. If students want to reply to others' questions, you're welcome to do that. I mean, just be respectful. Don't use the chat to abuse or attack other people. It's all a friendly environment here. Okay, so we'll start off with a brief introduction about the course, how we'll run the course, and then we'll right away get into the content. As you all know, I mean, you're probably used to the terms now, but we do have to move fairly quickly to get through all the content. So my name is Salil. I'll be a lecturer in charge for this course. Yeah, and that's the agenda for today. So besides me, there's a bunch of other people involved. So of course, our wonderful course admin, Ada. She's worked with me for a couple of years now, and we've done this course before. So I'm sure you'll benefit from her presence. We've also got 8 tutors. All of them have tutored this course before. They're well familiar with the content, so they'll also be helping and guiding you throughout the course. Okay, so in terms of the content, well, of course, as you perhaps all know, we will be using WebCMS. That's the web page. I do send out at least weekly, if not more, maybe bi-weekly notices. So please do keep checking the web page. These notices should get sent to your email that's registered in WebCMS. But for whatever reason, if you miss those emails, please make sure to check the web page every couple of days, right? Yeah, that's one of you saying about the joke here. That's a very clever networking joke. So this, I know we are kind of jumping ahead, but this is a special IP address, which is referred to as a local or home IP address. And addresses like this is not really address. This is what's referred to as a network mask, which we'll look at later. So in any case, that's a nice networking take on the current circumstances. Okay, so yeah, everything is here basically. I don't need to sort of guide you through it. Some of these tabs might not be visible yet to you. My view is slightly different to yours, but when things need to be released, they will be released. For example, the assignment is not yet out, so obviously you won't see that. For now, just focus on the lectures and labs and the homework questions, right? Now, do not post anything here on the WebCMS forum. That has been disabled. I've put a notice here. We will be using Ed. I realized I had forgotten to actually activate Ed, but I've done so this morning. So you should be able to start posting here. And I'll also put down a welcome post. Oh, the Ed invite link I sent was wrong, it seems. Oh, I'm so sorry. Yeah, this I should have been more careful. I will send out a fresh invite. Sorry about that. You should be joining the T3 forum, obviously, not the T2 forum. And in fact, I'll deactivate the T2 forum just so that there's no confusion. Yeah, my apologies. Okay, so this is, yeah, everything will be on the website. Just make sure you're checking it, particularly now, given that we are fully online. Just make sure you check the website, you're active on the forums, because that's how you'll get the most out of this course. So yeah, quick 30-second intro about me. That's me. My name is Salil. I've been here about 16 years, way too long. I do all sorts of things. My primary focus is, of course, to do some interesting research. So some of the areas I work on are Internet of Things, cyber physical systems, pervasive computing, security, blockchains and DLT, and machine learning as well, and all sorts of intersections amongst these topics. I've got a bunch of PhD students and postdocs and honors and project students working with me. Besides that, of course, I do teaching. I've taught a range of courses ranging from first-year courses to advanced postgrad courses. And this particular one is a favorite of mine, 3331931. In terms of admin, I look after all the PhD students in our school. Essentially, I manage various processes to do with their candidature. And whatever time I get left, I read up on science and technology. I like to listen to a lot of heavy music. I like to lift heavy stuff, so that's been impacted by the gyms being closed. But I try to do what I can at home. And of course, I really like to travel, but unfortunately, that's also not possible these days. So really hoping forward to returning to normalcy next year, like I'm sure all of you are. Okay, now the audience here. Well, this is a mixed course. So we have undergrads, we've got postgrads. I presume most of the undergrads would be second year, perhaps a few are third year. And I do know there's a bunch of students not from CSE. So mechatronics students in particular, some students from electrical engineering. We've had students from other faculties like business, science, and law take this course. Simply because it's if you find the topic interesting, it's certainly a very interesting course, and it doesn't really have a lot of prereqs, right? So all we assume really is that you have done some very basic data structures and algorithms, and yeah, you know some basic math, which you probably have covered in your high school, and you can program. So that is certainly one assumption we make. We do not teach you programming in this course. So we do allow you to work using one of these three languages, either C, Java, or Python. We will touch on some of the networking aspects of this, particularly the socket programming aspects, but we certainly do not teach you the actual programming languages as such, right? And being an introductory networking course, of course, we do not assume you know anything about computer networks. So this is really starting from scratch, as you may. So this is the text for the course. Now, I do know there's a new edition that just came out, the 8th edition, but we won't be using that because I'm not quite sure of its availability yet. So we'll stick to the 7th edition, which is shown here. It's a nice book. If you're interested in the topic, I would certainly encourage you to buy it. However, it's not, you can survive without having the text as such. There's enough material provided through the lecture notes. So really from the point of view of studying, you don't necessarily need the book, but I would still encourage you to get it. I believe the ebook is not terribly expensive. I think it's like $60, $70 Australian dollars if you buy the ebook version. So certainly something to consider. And then, yeah, there's a bunch of reference books listed here. So the aim, of course, is to gain in-depth introduction to networks. And of course, we use the internet pretty much as the vehicle to study computer networks, because that is the most widely used computer network. It's the most global computer network that we all use. And that makes it, I think, even more interesting, right? Because we are all of us use the internet all the time. But this course gives you an opportunity to actually look under the hood and understand how the internet actually works. I think one of you is probably not muted. Could you kindly turn off your mic? Thank you. Okay, and then of course, when we talk about learning the internet, as you'll see, a lot of it has to do with protocols. So we'll be studying various protocols. And beyond that, we'll be looking at the question of evaluating networks. So that's an important aspect, essentially the network performance. And also learning to do some programming, essentially write and design network protocols and network applications. And of course, this will give you a base to, if you're interested, do some further networking courses or research in that area. So the teaching learning strategies are fairly straightforward. We have lectures every week, 2 lectures per week, each of 2 hours. Labs, which will start next week. So there's no labs this week, even though your timetable may say so. The labs will start next week, and you'll see a few more posts on that in my notices later in the week. Beyond that, you'll be working on a programming assignment, so that should be fun. I'm still working on the spec. It should come out, I think, week 3 or week 4. That's what I've said. Maybe end of week 3, as I remember. And then, of course, to assess your understanding, there's a bunch of problem solving questions for you on the website. So yeah, everything will, of course, be online. We will be recording this. I do make recordings available on 2 platforms, just to, you can pick whichever one you prefer. I know YouTube might have some restrictions in some countries. So certainly we use Echo 360. That's the university provided resource, but I will also put all the lectures on YouTube, and both playlists are already linked to the lectures page. So you might want to bookmark your choice preference and look through that. Now, the chat does get recorded. Students in the past have asked about the chat. Now, unfortunately, there's no way for Zoom to actually record the chat window as such. So the chat gets recorded as a text file, and I will upload that text file to Echo 360. There's no way for me, easy way for me to do that in YouTube. So if you're keen to see what's happening in the chat, you might need to go to the Echo 360 playlist. Now in the lectures, we'll of course be covering all the important concepts, but I'll also try to bring in some of the current happenings in the world related to networks. So every now and then you'll see me talking of something that's happened in the news, some sort of a little bit of a tangent we might take on occasion to discuss some interesting things. And also we'll be looking at a bunch of problem solving exercises, right? Now, there'll be certain content I'll leave for you to study on your own. Most of this content won't even be on the exam, because these are sort of not so much interesting topics from an examination point of view. So this will all be indicated on the notes. And in order to gauge your feedback, whether you're following the concepts, we will be using quizzes, live quizzes. Now, in the past, I was using a platform called Zeetings. Now, unfortunately, Zeetings was bought by Canva, and they've actually disabled Zeetings. So obviously, all my quizzes went away with that. So I've had to build up a new repository, basically taking the quizzes and porting it to a different platform. And what we are going to do is use a new platform called Poll Everywhere. So again, this is the first time I'm using it. So let's hope it all goes well. And just to get the ball rolling, I might ask you a fun quiz. So can all of you please go to your, open a browser and type in pollev.com/Salil, and you should probably see something like this. Okay, it's working. Fantastic. That's great. Right. So which superpower do you think is going to be most useful for a UNSW student? I know this has nothing to do with networks, it's just some fun. We can afford that. Can you repeat this link? It's right here in the corner, pollev.com/Salil. You can't open it. I'm Yeah, I mean, there's about 60 students here. I've pretty much made it open, so there's no need to register or anything. Can you try again? Okay, it's working now. It's interesting. Most of you picked time travel. Maybe I should disable the from seeing each other's responses. I wonder if that influences the answers. Anyway, this was just some fun, right? So just to make sure it's actually working. It's interesting everyone chose time travel. I wonder why. Okay, so labs, as I said, they'll start next week. The labs are rather interesting in that they will try to reinforce some of the concepts we learn in the lecture. So we'll be using a bunch of networking tools. So tools like the Wireshark packet sniffer will be heavily used. Other tools like Traceroute, tools that allow you to send out DNS queries. And in fact, you'll also get the opportunity to set up a small network and do some experiments using this NS2 simulator. So I think these labs complement a lot of things we cover in the lectures, and hopefully you'll gain a lot of value out of it. So there'll be actually 8 lab sessions. 6 of those will be these lab exercises. These are all guided by your tutors. These are marked, and we'll take your 5 best lab marks, which then gets added up to form the lab component of this course, right? You need to submit lab reports. All of this is fairly straightforward. You'll find the instructions in the lab specs. We do encourage you to look through the labs before you actually show up to the lab. That gives you, that way you're better prepared, and then you can quickly move through the lab. In addition, we've also set up 2 tutorials. So these are the weeks right before your midterm and right before your final. And these will help you prepare for the actual exams, right? So in this tutorials, we'll give you some problems, and then your tutor can work through those problems with you, right? So there's a question, are labs recorded? Yes, they are all recorded. So if you go to the labs page, you'll see there's, I mean, some of your tutors prefer to use Teams, others prefer to use Zoom. I let them choose, I mean, whatever they prefer. But essentially here you'll see there's a link to the actual meeting, and then there's a link to the recording. So all of this will get populated, right? And of course, yeah, if you don't attend the lab live, you can always go back and see those recordings. The labs, you should be all using VLab. I know it's a bit fiddly. There can be some networking, delays, especially if you're overseas. But this is really beyond my control as such. VLab is something that's offered by the school, and they're constantly trying to improve that, right? So the recommended client is, of course, Tiger VNC, though you can use some other clients, and you can find all the details here essentially to set up VNC, VLab. If you need to set up a VPN, that's what you need to look at, and so on and so forth. And of course, you'll need to know some very basic Linux commands. I mean, nothing super complex, but if you're not familiar with command line Linux, I would encourage you to have a quick look at this link, right? Just enough so that you can work through the labs. In terms of getting help, Ed Discussions, the forum I showed you, is the best place to get help. One of you said I sent the wrong link. I do apologize. I'll send through a new fresh link later today. And you should have access to that, to the forum. So make sure you're posting questions on the forum rather than emailing us, because clearly other students will benefit from your questions. Other students can answer your question. And really, in this difficult time, that's the only opportunity we really have to build a community, right? So let's try to make use of that. We had some good fun last term. on Ed. So I hope all of you will also have some fun on there. And please do not post on WebCMS. The forum is disabled anyway. There's a question, what time before labs to the links open? Yeah, so usually it will be the Friday before. So this, for example, this Friday we'll open up the link for your first lab next week. Are any GUI tools needed on the CSV servers for the lab? I don't think so. I mean, for example, things like Wireshark, you could actually run natively on your machine rather than running it to VLab. So when we get to the Wireshark part, we've actually added that instruction that you might just be better off downloading and installing Wireshark on your machine, because that is a bit too resource heavy to run on VLab. The stuff you can run on VLab, like traceroute and all that, that should be fairly straightforward. And even some of that you could even run on your machine, right? So you'll manage. I mean, we are not doing anything complex GUI involved in this course. The labs are released on Friday, but they're due Tuesday the following week, right? So the lab for week 2 will be due in Tuesday of week 3. So there's a lot of time, right? So it's not the immediate Tuesday, it's the Tuesday the week after, right? The rest, if you want to email, use this email. Do not send me personal emails. I get too much email. And most importantly, the course admin can also reply, right? So you're not sort of restricted by my time. I do have to set up my consults. I'll do that this week and I'll announce the consult, so you can always drop in, and we'll arrange some extra consults for the assignments to help you, but that will all come later, right? Now your tutors are also going to be quite useful for you. So make sure you introduce yourself to them in your labs. Make sure you know how best you want to communicate with them. So really, I mean, that's for you and your tutors to decide, right? What if they prefer email, if they prefer you to post things on the forum, whatever, right? No. Sorry, there's a question here about email. So what I meant was, do not send me email, like to my personal email. Of course, the email should come from your UNSW account. That's the most preferred option, obviously, because we cannot know the veracity if you send us email from Gmail and all that. Just use this email if you need to email us, that's all. Yeah, so revisions based on my experience, generally the feedback was positive. I think for the most part, there was, students did request for some more support for the programming aspects. So this is something I do have planned for. Unfortunately, the turnaround time has been pretty poor. We barely got a week to rest, but we'll try our best and try to give you a little more support this time with programming. And the other point was to make more practice problems available. That said, we do have a lot of practice problems, but I'm happy to make 2 sample exams available, both for the midterm and the final. Okay, a few obvious things. I don't want to spend a lot of time on this, but just make sure we're all congenial to each other. Do not post anything offensive anywhere, be it email, be it the forums, be it elsewhere, outside I know all of you, I mean, students typically create their own groups for studying and all that, which is all fine. Just make sure you're following the standard code of conduct, and please be respectful to other students and to the course staff. This is another important thing to remember. Every term I teach whatever course it be, I always end up finding out, we run all your code through some plagiarism detection software, and of course most of the students do not do this, but there's always a small fraction who are perhaps not following these guidelines. So please be very careful about this. You're only cheating yourself, really, and there's a very high chance you'll get caught, trust me. So please do not resort to any of this, right? Okay, in terms of assessments, it's fairly straightforward. There are 40% of your marks are for the hands-on component, so that's the labs, and the assignment. There's just one assignment. It will be released end of week 3, start of week 4 roughly, and it will be due the Friday week 10. So there's plenty of time. Really, you'll see you're not going to really need 5-6 weeks to work on it, but just make sure you plan. At the same time, it's not going to be terribly easy. It's not something you could do in a day. So just keep that in mind, right? And as I said earlier, we allow you to use either C, Java, or Python, whatever you prefer, but we do not actually teach you those programming languages, right? And then of course the theory part, there's 20% for the midterm, 40% for the final. This way, I think having these 2 exams is good, because just having a single exam with 60% can be a bit traumatic. And also the midterm gives you a chance to sort of get used to the kind of questions, particularly if you're not used to this style of delivery. Remember, the exams are open book online, right? So the questions will not be something you can just pick from the text or pick from the lectures and answer. It's not a test of your searching ability. It's a test of your critical analytic skills, basically learning these concepts and applying them to a specific network or to a specific problem setting environment. So that's the style of questions we ask. So that having these 2 sort of midterm is a good preparation essentially for the final. So the midterm date is already set. So please mark this in your calendar. I know some of you may be working and stuff like that, but really I cannot take that as an excuse for the midterm. The date is already announced. So just mark it in the calendar and make sure you're aware of it, right? And of course, the final exam time, that will be decided by the exams unit, and we'll be told about it maybe 4-5 weeks before the exam. So I'll announce that once I know of the date. And for the exam, we'll be using this platform called Inspira. It's not very different from Moodle as such, right? But again, I'll have some practice exams for you to work through, so you're familiar with the environment. So there's a question, will there be coding in the exam? No, there won't be coding. It will just be problems. So to pass the course, yeah, it's fairly straightforward. You essentially add up all your marks. So there is one hurdle. You must receive at least 40% on the final. So that is a hurdle. It's not too difficult to pass this hurdle from past experience, but we must make sure that students are performing at a certain level on the final to allow them to pass the course. Now, how do you do well? Well, of course, you need to keep up. There will be a fair bit of content. I mean, this is how this course is. If I don't teach you content, I'm not teaching you computer networks. So this is a criticism we get sometimes, but I mean, that's how the internet is designed. That's how it's meant to be studied, right? There's a bunch of protocols and we need to understand how each of those protocols work and interact. So there's no way getting around that really, right? So there will be a fair bit of content. It's not difficult as such. It's just making sure that you're absorbing all that content. And most importantly, you do need to take a critical viewpoint. So this will become apparent as we move through this course and you get a feel for some of the homework questions and some of the sample exams that we'll release, right? So it's really all going to be about problem solving. And this doesn't necessarily mean heavy math as such. There might be 1 or 2 questions that involve math, but it's not really a math heavy course as such, right? And of course, make sure you're doing everything yourself and practice, right? Yeah, so the course will be fully online given the current circumstances. So I know this is difficult. it can be trying. It's probably been a whole year or more that you're doing online courses. But also try to put yourself in our shoes. It's also very difficult for us to deliver courses in this manner. So it's really all about all of us working together, right? So please make sure you are aware of all the deadlines. You do need to take some responsibility in keeping up with what is expected. Everything is there for you. I mean, the website is really your go-to point, right? So everything will be available. I'll make sure you're getting regular updates. We'll keep giving you feedback, and we'll be very active on the forum, right? But in the end, you do have to take some responsibility yourself, right? So just, yeah, just be patient, just be aware, and we'll all get through this, I promise. Okay. Yeah. What is this course about? Okay, so yeah, this is of course a very introductory course in networking, and really there are two parts to this. So there are certain key principles that govern how how networks work. So we'll be looking at a lot of those principles, and once we understand those principles, we'll see how they actually get put in practice. And to do that, of course, we use the internet as the vehicle, right? Because that is really the global network that we all know. And it's a fairly complex network. I mean, as you'll see, I mean, we'll dive right into that in just a few minutes and start understanding. But hopefully you appreciate that it's a fairly complex system. It's perhaps one of the most complex systems that mankind has ever designed. So in order to study this, we really need to sort of set up nicely and sort of have a structured approach to understanding these networks. So we'll be looking at what are the organizing principles. We'll be looking at various applications. So simple things like browsing the web. I mean, all of us take that for granted, but what's really happening under the hood, right? So that's something we'll be looking at. There's all this alphabet soup when it comes to protocols. So we'll be sort of studying each of this in a fair amount of detail. And while doing so, we'll also be looking at some fundamental aspects of networks. I mean, the internet it dates back to the late 60s. That was when the first 68, 69, that's roughly when the first global computer network was set up, right? So it's been about what, 50 plus years. So over these 50 years, there are certain important fundamental concepts that we have all identified as being really important for networks to function. So we'll be understanding those concepts. We'll be looking at how do you design solutions to address certain key issues that we face in designing networks, and evaluating the various design strategies. And most importantly, we'll be looking at how do we evaluate network performance, right? Because in the end, setting up a network is fine, but if your network is giving the users a crappy experience, then what's the use, right? So we always will take a performance-centric view of networks. Now, if you like what you study here, there's a bunch of other networks or network-related subjects that we offer here at CSE. So there's some of these advanced networking courses. There's a bunch of security courses, which that's the starting point, but then there's a huge number of other security courses that have also been designed. And then, of course, if you're really interested in this topic, you could all, of course, do a project with us, a thesis or a coursework project or a research degree. Yeah, so that's all I have to say about the introductory part. I will subject you to a lot of memes like this. So just a warning, there'll be a lot of memes and bad dad jokes that you'll hear throughout this course, right? So I'm sorry, but that's just the way I am. So you'll have to suffer through that a little bit. Okay. So let's now start looking at some actual content. Okay, let me just finish up my coffee here. Right. So here we go. Yeah, first up, acknowledgement, of course. A lot of the core content is from the authors of the text. So the text I mentioned, they have also kindly given us a set of lecture slides. So of course, we use that as a starting point, but we've added a lot of our own content to these slides as we move now, as we've sort of taught and refined this course, right? So this is really what we'll be looking at today. And the next lecture this week is just to give you a big picture, right? So just to introduce some of the key terminologies, what the internet is about, what are the various elements of the internet, and also what exactly do we mean by performance? What are the things we need to be looking at? What exactly do we mean by protocols, and so on and so forth, right? So this is just to give you a feel, really. A lot of these concepts will be covering in a lot more detail as we go through the course. So please do not feel alarmed if some of this seems a bit unclear at this stage, right? Because yeah, we'll be really diving deep into all of these concepts later. And yeah, of course, we'll be using the internet as our vehicle for understanding all of this. So let's start by looking at what exactly.
Terminology.
Okay, guys, you need to make sure you're muted. Let me just see if I can make sure everyone's muted. Okay, seems so. Okay, yeah, so we'll start off by looking at what is the internet and what are protocols. So right up here, you'll notice there are two things in this introduction that I'll not cover. So the book has a very high level introduction of security. So this is so high level that really you don't need me to cover that for you. So you can certainly read that on your own. And really there's no questions I can ask you on that. It's just too high level. And the second bit is the history. Now, of course, that's nice to read, but I can't be wasting time here, valuable time. So that's something I'll leave you to look at. And there's also this very nice internet timeline if you're interested to look at. Okay, so let's start off by a quick quiz. And let me ask you, what do you think, how would you define the internet? So if someone asked you, could you define the internet? How would you actually define it? Let me just open up that quiz for you. Okay, so if you could go to polev.com/Salil, and could you select one of these answers? If you select the last one, you'll have to type your answers in Zoom. I couldn't find a way to allow you to type something in PoleEV when I have a MCQ question up here. So again, the URL will always be polev.com/Salil. Okay, let's see how's everyone going. Okay, so most of you said number 2. Number 3. Now, the correct answer is actually both of these. So this was kind of like a trick question, and we'll be actually exactly looking at this in the next slides, right? So one of you has answered here, connect bamboozled. Okay. a connection between two or more users for data transmission. So yeah, that could be one way to describe the internet. So let's start by taking what's referred to as a nuts and bolts view, right? So essentially, what are the various components, be it hardware, be it software, that sort of make up the internet, right? So we'll use this simple abstraction to represent the internet. And we'll start off by looking at what's referred to as the edge of the internet, right? So if you were to abstract the internet like this, the edge is essentially all the end devices, all the computing devices that we connect to the internet. Now, traditionally, when the internet was developed, these were strictly workstations and servers, right? However, over the years, we've started connecting all sorts of devices to the internet. And I'll have a slide later about these end devices. But as you see in this picture, you have, of course, traditional devices like computers, servers, larger servers. This might be a desktop, a laptop, but then phones. And now with the rapid escalation of this whole notion of Internet of Things, we could have traffic lights. I mean, there are in fact traffic lights today that are connected to the internet. There are cars that are connected to the internet. So we have what are these end systems, which are often referred to as hosts. And these are primarily running some networking applications, right? So that's why they're called hosts, because they're hosting networking applications, right? So that's the edge. Then if you look at the internet itself, we have some devices which we'll for now refer to as packet switches. There are actually broadly two different kinds of packet switches. We have what are referred to as routers and what are referred to as layer 2 switches or Ethernet switches. But for now, we'll just group them together. We'll look at those differences a little later in this course. So we have these packet switches, which are essentially responsible for forwarding your packets, right? And there are probably millions of these packet switches that make up the internet. Now, of course, we can't just have switches and hosts. We need some way to connect all of them together. And this is where the communication links come into play. So these, again, there are various kinds of links. So we have fiber links, we have copper, we have radio, we have satellite. So there's a host of links that are available. Some are like physical links, some are just radio. So when you're transmitting Wi-Fi, there's no real physical link as such, right? You're just transmitting electromagnetic waves. And all of them vary in the data rate. So the rate at which you can send data, which is often referred to as bandwidth or transmission rate. And finally, we need some way to organize all of this. So that's where essentially the networks come into play. So this is more sort of organizing all these devices and controlling and managing those networks. So for example, here you have a mobile network. So this is something that say Optus or Telstra sets up. You have the network in your home. You might have the network here, say on the UNSW campus, or maybe in your company. And then we have what are referred to as local or regional ISPs. ISP stands for Internet Service Providers. And then we have similar ISPs that work across a more global or national scale. And then finally, we have content providers, right? So these are the companies that are actually providing content like Google, Amazon, Netflix, you name it, right? So they have set up these data center networks where they're hosting all this content, right? There's a question here. Is it possible for you to provide step-by-step slides? Okay, I'll see what I can do. I'll have to have a look at that. What is the difference between a router and a switch? Yeah, so as I said, don't worry about that right now. Very briefly, a router works at layer 3, a switch works at layer 2. It's just too hard for me to explain the differences so early in this course, right? So please bear with me for now. We'll come to that later. Right? Okay, so yeah, so what are these there's a question layer 2 and layer 3 of the OSI model. So there's this 5-layer model, which we'll see in the next lecture. So it's slightly different from the what's referred to as this OSI model. I will talk about those layers in our next lecture, right? So again, it's very nice that you're all asking these questions, but it's hard for me to jump ahead a little bit without covering some of this introductory stuff. Okay, so what devices are we connecting, right? So of course, we have the traditional devices, but I'm pretty sure a lot of you have one or more of these kind of devices, right? So these are all essentially non-traditional devices that are being connected. So things like cameras, your, what do you call these, voice assistant speakers, smart fridges, smart photo frames, content streaming devices, even pacemakers, light bulbs, smart meters, cars, wearables, glasses, and some crazy things like this toaster, which toasts your toast based on the weather, if you're too lazy to even check the weather, perhaps. So in any case, there are all sorts of interesting devices that are being connected, right? So, and there's all, essentially, we've reached a point where we have billions of devices nowadays being connected, and this trend is only going to keep increasing. So you'll see slides like these where these strategists sort of try to estimate how many devices will be connected to the internet. So we are roughly here, right? So that's, I think this is already too low. We are probably already, now maybe we are right. So this is around 30, am I reading this right? Yeah, 30 billion roughly, right? So that seems about right. And it's estimated to go up almost to 40 billion or so in just 4 more years, right? And of course, these are some of the devices that you see as an end user, but there's a lot of devices in factories, automation, machinery that is being connected to the internet. So this is not even visible to us as end users, but if you're working in those sectors, you'll see that a lot of things on the factory floor and in manufacturing are also being connected to the internet. Right? Okay, so continuing our nuts and bolts view. So really, if you think about it, the internet is not really one global network. It's all these networks which are somehow interconnected together, right, through these ISPs. And we'll be looking at this structure a little bit later this week. The next piece in the puzzle is what are referred to as protocols. So again, just give me a minute and I'll dive a bit more into protocols, but essentially protocols control everything. All messages that are sent and received on the internet are following certain protocols. So whatever application you might be using, for example, if you're currently browsing the website of the course, you're using the web, which runs on HTTP, which runs on top of TCP/IP. And below that, there'll be some link layer protocol. Maybe if you're connected through a Wi-Fi network, then it's Wi-Fi. In my room here, I've got Ethernet. So I've got an Ethernet cable connecting my laptop here, and so on and so forth, right? So everything is governed by protocols. And these protocols are particularly the ones that are open, or essentially open standards, as they are called, are managed by an organization called the IETF, the Internet Engineering Task Force. And the actual protocol spec you'll find in something referred to as a RFC. So there'll be in fact, there'll be multiple RFCs for HTTP, there'll be RFCs for TCP, there'll be RFCs for IP, UDP, and so on and so forth. So the name originates from, there's a bit of history to that. So in the 70s, when the internet was being developed, they used to write up the spec and send it out for comments to other researchers. So that's why it was called request for comments, but the name has stuck essentially. That said, there will be other protocols which you'll never see the specs for. So these are what are referred to as proprietary protocols. So Skype, for example, Zoom, these are all essentially proprietary protocols, right? We may have some understanding of how they work, but we don't necessarily know all the minute details, right? So that's one viewpoint, right? So where we consider all the components that make up the internet. Another viewpoint to take is particularly when you think of someone who's actually designing networked applications, right? So from an application developer's perspective, the internet is just providing the application developer certain services, right? So the application designer comes up with a brilliant idea. Hey, I want to design this web streaming application, or teleconferencing, email, whatever the application may be. So the internet essentially then provides a programming interface. There are certain APIs, standard APIs that these application designers use. And in fact, you will use when you develop your own assignment. And these APIs essentially serves as hooks, right? So these APIs allow you to send and receive messages, application messages into the internet. And you're then using the services that the internet provides to transport those messages from one end of the application to the other end, right? Remember, your application is always distributed. When we are talking of networked applications, we are writing programs that run on different end systems, and then they're sending and receiving messages to each other, right? So something like this. So you might have, say, an entity Alice who's sending a message to Bob, and Alice and Bob are essentially using the APIs, the standard APIs provided by the internet to do that. So this is essentially a service-centric view. And the beauty of this is it has allowed us to develop all sorts of interesting applications, right? Because all it really you need to do as an application designer is you don't have to worry about any of this. You abstract away all the details of the internet, you use the standard APIs, and all you do is write programs that run on different end systems or different hosts, right? Okay, so let's move forward now and take a quick look at what exactly do we mean by a protocol, right? So as humans, we are actually using protocols all the time, right? If you think about it right now, I mean, even in this remote setting, there's an expectation that I'm the lecturer, so I'll be doing most of the speaking, and you'll be listening in. And if you have questions, you'll be typing them here in the chat, and then I'll be looking at the chat and replying, right? So this is a sort of protocol we are following. Whenever you ask someone what's the time, obviously, assuming that person knows what time is, they would reply back, right? So things like that. We're constantly using protocols. There are messages we send and certain actions we take, and so on and so forth. A lot of this is sort of unconscious, but if you think about it, we're doing that all the time. On the internet, the same applies, except here, it's not necessarily humans, it's computing devices that are sending messages to each other, right? So all activity on the internet is essentially governed by protocols. There could be hundreds, in fact, there could be thousands of protocols that you'll find out there, right? So in a very abstract sense, if you were to ask to define a protocol, you would say that a protocol actually defines the format, essentially how the message should look like, what are the contents of the message, and the order in which those messages are sent and received amongst these networking entities, right? So one computer may send a particular message following a particular protocol to another computer, and then this computer will respond back with an appropriate message, and so on and so forth, right? So all of that is actually defined in the protocol, right? So here's some very simple examples. So this on the left here is what we refer to as a human protocol, right? So a person says hi, the other person replies back politely, asks for time, replies back with the time, right? Now, when you're actually browsing the web, so this is a quick peek at what's actually happening. So when anytime you're requesting a web page, by you, I mean your browser is requesting a web page from a particular website, the first thing that actually happens is a TCP connection gets set up between the two endpoints. And yes, one of you has pointed out a TCP connection setup actually requires a three-way handshake. Now, till we start looking at TCP, we'll abstract over that third part of the handshake, and we'll just assume it's a simple two-way handshake. But we'll explore the exact way this is done when we actually get down to the TCP part of this course. So for now, we just assume, okay, a TCP connection is set up, and then a GET request is sent for the web page, and then the server responds back with the actual web page, which then gets displayed in your browser. Right. So this is a very simple illustration of two protocols in action: first TCP and then HTTP. Right. And we'll be looking actually a lot of these pictures in this course. So this is what's referred to as a timing diagram, where we'll have, say, a source, a destination, and then we'll map out how the messages actually flow, and time moves vertically, right? So we'll keep revisiting these pictures throughout this course, really. Okay, so let's take a bit of a breather. In fact, this is a nice point to actually take a break. So what I'll do is I'll set up this quiz for you. This is just, again, for you to think about how many internet connected devices you actually have in your home. So have a little bit of a think about this. I should be able to move through these here, right? Yeah, there you go. So have a think. And at the same time, let's take a quick 5-minute break. So if you want, feel free to sort of walk around a bit, get a sip of water, whatever, and I'll be back in 5 minutes, and then we'll commence the lecture again. And in the meantime, please do answer this question as well. So I'll see you in 5, and I'll also pause the recording while I'm at it. Okay, okay, we are back. So let's see what you've answered. So most of you've got between 10 to 20. There's someone who's got more than 100. Is that really true? That's a lot. Yeah, I was thinking myself, I think I'll be in this category, roughly. That's what I've got at home. Yeah, in any case, this was, again, just some bit of fun. Right, so now that we've looked at how the sort of just very briefly taken a high-level view of what the internet is about and looked at protocols, let's now dive a little deeper and start by looking at the edge of the internet. We already talked about the end systems, also referred to as the hosts. So remember, the hosts primarily are there for running applications, right? And as you'll see later, typically, not all, but a lot of applications use this client server model, essentially. So in those kind of applications, you would have dedicated devices which run as clients, and then dedicated devices which run as servers, right? So it's important to appreciate that both clients and servers essentially make up they're at the edge of the internet, right? Sometimes people think the servers are sort of not sitting at the edge, but really they are, because these are the endpoints, right? So your messages originate from the client, they reach the server, then the servers respond back with messages from the client. Someone is saying no audio. Is that true? Is my voice not audible? Okay. Yeah, you scared me there. Okay. Yeah, so yeah, sorry, I broke my chain of thought. Yeah, okay, so the clients and the servers, right? So even though you might have that distinction, remember that both clients and servers sit at the edge of the internet. The servers are often located in data centers these days, right? So that's been the typical model these days, where rather than setting up your own servers, many organizations sort of prefer to host them in data centers, which are sort of dedicated physical entities where they're hosting a lot of services essentially. Next, we have what are referred to as access networks. So these are the networks that allow these end systems to connect to the internet. So these are what are often referred to as the last hop. So the last hop between, say, you and the internet, right? And again, these could be varied. So we have the traditional sort of wired setups, particularly in organizations, in offices, where you might have your computer connected to Ethernet cables, which are connected through Ethernet switches, uh, maybe a collection of Ethernet switches, and then some routers, and then to the backbone. Or you might have wireless links, like say in your home right now, many of you might be connected through an access point. Oh, wow, 802.11 access point. So your last hop is essentially wireless. Your access point very likely is connected through a wired network, through either ADSL or cable or fiber to the rest of the internet. And then we have what's referred to as the core of the internet. So this is a maze of interconnected routers. So this is multiple networks that are sort of roughly organized in some hierarchy, going from, say, local or regional coverage to national or global coverage. And then we have these content providers also in the mix, right? So now the question is, how do we actually connect the end systems to the edge routers? And again, there are typically three broad categories of this. So the first one being what you have in your home. So that's the residential access network. What you have in organizations, so say like schools or universities or companies. So that's institutional access networks. And the third category is mobile access networks, right? So these could be either Wi-Fi or, say, cellular, so 4G or 5G. And there are certain distinct differences in terms of what these networks provide. So the first key dimension to look at is what is the data rate, or what's the transmission rate, or also referred to as the bandwidth, right? So how much data can you actually pump into these networks, which is measured in bits per second. And then the second issue is whether the network is shared or dedicated. So a very good example of a shared network is Wi-Fi, right? So when you're connected to a Wi-Fi access point, your transmissions are actually broadcast. So potentially, if there are other users also connected to the network, you're sharing the network with them, right? So it's not just a dedicated link, unlike, say, if you have a Ethernet cable, like right now I'm connected my laptop through an Ethernet cable. So there's a dedicated Ethernet link between my machine and my switch and router there at the back, right? So that's just exclusive to my machine. It's not being shared. So let's start off by looking at a very common access technology referred to as DSL, Digital Subscriber Line. Now, of course, the goal here is to just give you a brief overview, right? We are not sort of going deep into all the finer grain details of how DSL works and all that. Some of this goes into essentially what's referred to as the physical layer of the network protocol stack. And in this course, we don't actually go down to the physics, because that's typically the domain of electrical engineering, telecommunications engineering. So we'll abstract over some of those lower level details, right? So here we are essentially using existing telephone lines. So essentially the copper that's laid out all over wherever you're located, and essentially using that copper, which was originally put in for the physical telephones, the old school telephones, and using that to transmit data, right? So typically when you have a DSL network, you'll be given a DSL modem, and you'll also have to set up a splitter. So this splitter essentially splits up the bandwidth so that some of the, whatever part of the bandwidth is being used for telephones gets sent to the telephone network, the rest gets sent to your DSL modem, and then you can send and receive data through your DSL modem. Right, so this is all done using what's referred to as frequency division multiplexing, or FDM. So the idea here is pretty simple. There's a certain range of bandwidth over which you can actually transmit on the copper spectrum. So the way this is set up is part of the channel is reserved for your telephone lines. So PSTN here stands for public, oh no, what does it? I'm forgetting the acronym, but it's essentially the telephone network, right? The telephone network. So that's the lowest band of the frequency is reserved for voice. So the splitter actually takes this lowest part of the spectrum and sends it to the telephone line. The rest of the capacity is actually used up for transmitting data. And in most instances, you'll find that this is actually asymmetric. So that's where the A comes from. So a small part of the spectrum is reserved for upstream or uploading. The rest of the bandwidth is reserved for downloading, right? This is because typically most of us are downloading a lot more data than uploading, right? Yeah, that's how essentially ADSL works, essentially. Oh yeah, public switch telephone network. Tim, thanks, Tim. Yeah. One of you is also making a good point that these days a lot of us are, who's that, Jack? Yeah, so Jack is saying a lot of us are actually also creating content, right? So for example, if you're using Twitch or if you're streaming live on YouTube or whatever, like right now, I'm actually streaming this from my home, right? So yes, so this traditional approach of having a lower capacity for upstream is kind of also a bit old school these days, because a lot of us are also generating content, right? But in any case, that's how ADSL was originally set up, though it is also possible to get DSL subscriptions where you can have more upstream bandwidth. So basically roughly equal to downstream. And then essentially there's what are referred to as DSL access multiplexers. So essentially multiple homes connect to these access multiplexers where all the data is essentially multiplexed, and then the DSLAMs are essentially connected to the core internet through some other ISPs, right? And part of the bandwidth is connected to the telephone network. So essentially this lower frequency band essentially is connected to the telephone network. The rest of the channel capacity is connected to the internet as such. Right? And these are roughly the typical data rates you get. The actual data rate you get may vary a little bit because there's also the distance factor, right? So the further away you are from the DSLAM, typically the lower the bandwidth you can get. So this is something I picked up for PPG from around campus. I'm not sure if this is completely up to date, but this is roughly what it showed maybe 2-3 months ago when I got this screen capture, right? So you'll notice if you're within say 1.5, again, these are all estimates, it's not highly accurate, but the closer you are to the DSLAM, the higher the data rate you can get. So there's a point here made in the chat by Zain. Isn't that why businesses are set up with more streaming bandwidth? So yeah, certainly these days, because a lot of us are generating content, this asymmetricity may not necessarily hold anymore, right? Again, remember the DSL technology dates back to, I don't know, 20 years, maybe roughly something like that. So yeah. So there's a question, does that mean the red regions in the map are better? Yeah, so again, this is an approximation, but you would get better data rate if you're closer to DSLAM. So the red part, as it says here, typically you would get a better data rate, as you see here, compared to say the yellow part or the green part, right? So DSL is one option. The other option is to use cable. So something like Foxtel, for example, here in Australia. And the concept is really similar in that, again, the capacity, the bandwidth over which you can transmit data is split up. So part of the channels are used for cable, essentially video, and the remaining channels are then used for data upstream and downstream. Yeah, so conceptually, this is again same. You would need a splitter, splitting up, say the video channels get sent to your TV, the data channels get sent to your computer, and so on and so forth, right? The actual network itself is a combination of fiber and what's referred to as coaxial cable. So the actual cable coming into your house is coaxial, but then in the back end, they also make use of fiber to get better data rates. And the typical data rates are, as you see here, ranging from say 40 megabits to 1.2 gigabits for downstream and say 30 to 100 megabits for upstream. Right? Now, one distinction with with cable is that unlike DSL, which is dedicated, cable is actually a shared technology. So the amount of users on the cable network will determine the actual data rate you get. So if there are many other users on the network, say in the evening, the actual data rate you might experience will be lower than say during off-peak times. So that is one distinction compared to DSL. There's a question on what does DSLAM do. DSLAM is basically aggregating all the traffic. Where's that picture? Yeah. So it's basically a aggregator, access multiplexer. So it takes all the channels coming in from multiple homes. It will again do the splitting. So it will split up part of the channel that's meant to be connected to the telephone network, to the actual telephone network, and the remaining channels get connected through routers to the rest of the internet, right? So it's sort of like an aggregation point where you're aggregating data and voice from multiple users and then connecting it to the appropriate networks, essentially. Okay, the third typical option that's come up is fiber, right? So this is again something fairly recent in most countries. So here in Australia, we have the NBN. In other parts of the world, you have different technologies, different companies doing this. But again, there's a bit of variation in terms of where the fiber point actually ends. So if you're really lucky, you have fiber all the way to your home. So that's referred to as fiber to the premise. Most of us would have some close by endpoint. So this could be, say, a node that has been installed maybe just a few meters from your home, or say in your building, or something like that. So you have fiber up to that endpoint, and then the last mile essentially may just be either copper or cable that's connecting your home to that endpoint. So there's these various combinations like fiber to the home, premise, or curb, essentially. And roughly, in most instances, you would get much higher data rates, both upstream and downstream, with fiber. Because simply put, this has a lot to do with the physics. So when you're transmitting data over fiber, the actual data is converted to light pulses. And by doing so, you can actually pack a lot more data in a thinner cable, essentially. That's again all to do with the physics, which we'll kind of abstract over in this course. Let's see, there's a couple of questions. So the splitter separates phone data and voice into different frequencies and DSLAM sends them to different places. Yeah, roughly you could say that. Why is the direction from home to ISP inside DSLAM? I'm sorry, I don't quite get direction as such. I mean, this is just showing upstream, right? I mean, similar things would happen downstream. So it's just sort of an illustration of the upstream part, but of course there would be similar things happening downstream, right? So yeah, it probably should be bidirectional. You're right. Joseph is saying after fiber was installed, my download and upload went down. That's too bad. You probably need to contact your network provider, right? And then there's a question for ADSL, the bandwidth is not shared. Yes, that is correct. So ADSL is not a shared technology. Cable is a shared technology. Fiber is not a shared technology again. So irrespective of whether you're using DSL, cable, or fiber, I would think this picture is a good abstraction of how most of your home network looks like. Correct me if I'm not wrong, but you either have an ADSL, a cable modem, or a fiber modem that's connecting you to the rest of the internet. You have a router. Essentially, it's also functioning as a NAT. Now, don't ask me what is a NAT right now. We'll get to that a little later. And then you might have, say, some Ethernet cable connecting your router to your computer. You might also have an access point that's connecting various wireless devices to the network, right? Now, of course, in reality, even though I've shown these as different entities, very likely you might just have one or two boxes which are combining some of these functionalities, right? Which is so the exact mechanics of that may vary a little bit in terms of the abstraction, but this is very likely how your home networks looks like. There's a question. If the last mile is copper, not fiber, won't that create a bottleneck if the speed is to some extent, yes, that can, but typically the fiber is getting very close to your home. So it's definitely much closer to you than, say, the DSLAM, right? So in that sense, yes, you might not be able to get gigabits, but you'll still get appreciably more data than, say, ADSL or cable. Yeah, I think Joseph has also answered this. Yeah, NBN and TPG, these are just companies. You don't need to worry about that. So TPG is an ISP. NBN is the entity that's actually installing the fiber here in Australia. They often resell to other ISPs essentially. Okay, so that's the wired part. Now, in the context of wireless, again, there are two broad distinctions. And remember, in a wireless network, you always need a device which you don't normally see in a wired network. So this is what's referred to as a base station or an access point, right? So that connects all the wireless devices to the rest of the internet. So we have on the one hand what's referred to as wireless LAN or 802.11 or Wi-Fi as we all know it. Typically, this is used in enclosed areas. It can also be used outside buildings, like on campus, for example. The range is roughly a few, maybe up to 100 meters at most. A lot of it depends on the terrain because wireless signals often, in the way they propagate through various medium can vary. So if you have got a lot of concrete and stuff, a lot of steel, then it may not get through that. Whereas if you have a little more open space, it may be easy for it to propagate further distance, right? Now the Wi-Fi standards, originally they were using all sorts of alphabet soup and they still do. So I think the current standard is something like AE or something like that, but they've now simplified it for end users and they just call it with numbers. So we are currently about getting into Wi-Fi 6, which is the latest standard. And of course, the main variation is again in the physical layer. So what is happening is Wi-Fi is they're coming up with very clever ways in the physical layer to use technologies like what's referred to as OFDM, MIMO, and so on and so forth. Again, we won't get into all of that because that gets into really electrical engineering. But that's where all the innovation is happening, essentially to speed up the data rates. So even with Wi-Fi these days, you can get fairly high data rates in most cases. Right? And then the other side is what's offered by your mobile providers, right? So this is mainly for wider area. So it's the coverage is up to kilometers, and this is done through base stations, right? And of course, one key distinction here is with wireless LAN, we are using part of the spectrum that is open. So we don't really need any permission. Anyone can set up their own access point. Whereas cellular, the spectrum that's used is restricted. So only certain companies can get access to that. And then when we want to use these bands, we need to pay these companies to be able to connect to their network. Right? So companies like Telstra, Optus, and so on and so forth are cellular access providers. And then we pay them a certain monthly fee to be able to use their networks. And here we have these intermediate entities called base stations, which usually cover several kilometers. And then as long as you're within the range of a base station, you can continue to send through that. Once you move, you typically get handed over to another base station, and then you can still enjoy connectivity. Right? What's the meaning of BGN? So yeah, as I said, these are all alphabet. These are the standards essentially. The various improvements in the Wi-Fi standards that are happening. You don't have to worry about all of that. They are just different versions here, essentially. Okay, so that's the wireless part of the access network. The third thing to look at is in an enterprise setting, right? So this is what you would normally see, say on campus, in a company, and so on and so forth, where you actually will have a mix of wired and wireless access. So on campus, for example, there are over 5,000 access points deployed, which gives us the unified wireless network. But there's also a fair bit of Ethernet connectivity. So I remember in my office, there's a couple of Ethernet connections that I can connect my computers to. And there's lots of Ethernet cabling run all through CSC, right? Now, normally you would get higher data rates through Ethernet because you can go up to several gigabits. With Wi-Fi, you can just about start touching gigabits. So normally with Wi-Fi, you'll get a little lower. Again, with Wi-Fi, the access is shared. With Ethernet. You're not really sharing the network with anyone else, because this Ethernet cable, for example, is dedicated for your machine, right? You're not really sharing it with anyone. So these are some, I did some speed tests. I think I did this, when was this? Oh, it's a bit dated actually. Oh yeah, I actually noticed these, the bandwidth hadn't changed for the past couple of years. So I did do a test earlier in June, and I was getting very similar data rates on all my networks. I don't know if that's a good or a bad thing, if in 2 years the bandwidth hasn't changed, but this is what I was getting then and earlier this year as well. So this is showing you, for example, my home setup. That's what I got on Unified. That's what I got in my office on Ethernet. And that's what I got on the Optus network on a 4G. So you see some differences, right? So on campus in my office, I usually get the best performance. Unified is about one order low. My home network is slightly lower. You'll notice my home network is asymmetric. compared to, say, these are not so asymmetric. And then 4G is actually not bad. I'm actually getting higher data rate on a 4G network, say, than even my home network, right? There's a question, does that mean if you connect your home network with Ethernet to your home modem, would the speed be faster? Well, I mean, it depends on the backend, right? Like here, for example, you see I'm connected on my home network through fiber. It's dedicated, no one is using it. But that's not necessarily giving me higher data, right, than say a 4G network. So really it depends on the actual pipe that's connecting to your network, right? So yeah, then just where is a Wi-Fi extender placed in the internet structure? Well, that's just an additional relay, right? So you might have an access point, and then to improve coverage, you might have an extender or a relay that allows, say, other devices who may not be able to directly reach the access point to get connectivity. So there's this whole notion of meshed wireless networks that coming about. So products like, I believe, Eero, and there's a bunch of other products where you can essentially deploy multiple access points, if you may, or you could call them as extenders, and they allow you to extend the coverage over your home, particularly if you've got a large home. And particularly if you have spots, say, due to the building structure and so on, where Wi-Fi cannot easily penetrate to some of the rooms. Okay, so let's have a bit of a breather. Let me ask you, what is your connectivity looking like? So if you could kindly go back to so could you kindly answer this? Oh, I should activate it. Sorry, just give me a sec. So there's a question, Ethernet is dedicated or shared? Ethernet is dedicated. I mean, the way it's current, it is possible to set up a shared Ethernet network, but no one sets up Ethernet networks like that. So as you saw in that picture, there's a Ethernet switch, and then there's direct connections from computers to that Ethernet switch. Right? Well, you should know this. Maybe you could look it up, what technology your ISP is offering. If you don't know right now, that's okay, but that's something you can find out. Maybe check your ISP's website to figure out whether you're using ADSL. It's very likely going to be one of these three. I mean, if you're using 3G, you would know, because that's something you would have, or even satellite, knowingly purchased, right? Okay, so let's have a quick look. Wow, this is really interesting. So this has changed. For example, last year, I distinctly remember fiber was, I think we were roughly split between DSL and fiber. Cable was close. But this is really interesting that a vast majority are on fiber. This is great, actually. That means fiber penetration is certainly improving, which is very good to hear. Though particularly here in Australia, we've been pretty bad with, or slow, I should say, with the fiber rollout. But it's really good to see that a lot of you are on fiber. It's interesting that one of you is on a satellite network. Perhaps this person is on a remote area. Okay, so let's keep moving forward. Yeah, there's this bit on the physics, the physical media, which I'm actually going to skip. As it says here, I'm not going to ask you questions on that. This is just really for your information. So certainly read through it if you've got the book, or glance through these slides in your own time, but I'm not going to really spend time on that. What we'll now do is we'll start looking at a fairly important concept on how the core of the internet is designed. And we'll actually look at two technologies. So the current internet uses a technology called packet switching. And as the name suggests, the idea is fairly straightforward. So by the core, by the way, I mean these routers, right? So we've looked at the end hosts, we've looked at the access networks. Now, what glues together the access network is these network of networks that actually make up the core of the internet. So what we are looking at is how is the core network actually designed. So currently the internet uses a technology called packet switching. And the idea is fairly straightforward. The hosts break up the application messages into smaller chunks. These chunks we refer to as packets, as a generic term of these chunks. And these packets are forwarded from one router to the next across this maze of links, across this maze of routers, till the packet actually reaches the destination. And when a packet is being transmitted, it can use the full capacity, the full data rate of that particular link that it's being transmitted on. Now, going back to the 60s, when the internet was being designed, there was actually a competing technology which is called circuit switching. So there was actually a bit of a tussle. So there was this people who were pushing for circuit switching, and these people actually came from the telephone networks, because the legacy telephone networks use circuit switching. So, I mean, if you go back to the 60s, if that was the only technology in use, so it kind of made sense to them to continue using that technology for the internet. And then there was this other camp who was pushing packet switching, right? And they were competing, and there was a bit of sort of back and forth between them. Now, obviously, packet switching won, and that's what we use. But it's still instructive to have a quick look at circuit switching and understand why circuit switching was not chosen, right? So that gives us a bit of insight into why the internet is designed using packet switching. So let's first look at circuit switching, understand why it was problematic, and then we'll look at packet switching. So the name circuit switching essentially, again, since it comes from the telephone network community, you'll see the reference to, what's referred to as a call here, right? Because again, the origins of this are from telephone, the telephone networks. So in telephone networks, of course, we are placing calls, right? So the idea here was to actually set up an end-to-end connection, essentially, or if you may, an end-to-end circuit as such, between the source and the destination, right? Which meant we had to explicitly reserve certain resources. And by resources here, we really mean part of the bandwidth, right? So we are explicitly reserving resources along the entire path from the source to the destination. So here, for example, we reserve resources on this link and on this link, and so on and so forth, right? Now, the problem with this is if you're reserving these resources, it means these resources cannot be shared. So which means once you have set up that reservation, only you can use that part of the channel, right? So for example, if you reserve 1 megabits, and let's say the capacity of this link is 4 megabits, I'm just making up numbers. It means that 1 megabit that's been given to you cannot be used by anyone else. So effectively, only 3 megabits is now left on that link, right? And this is problematic because if you're not actually making use of that capacity, then it's just wasted, right? No one else can use it. And this is a big problem, because remember, when you're transmitting data, it's not as if you're constantly sending data, right? You might set up a circuit. Hypothetically, you might send data. Let's say you're browsing the web, you might fetch one web page, you might actually look at the web page, then you might fetch another web page and stuff like that, right? So you're just wasting resources when they're not being used. And this is a big problem with these circuits. So the typical way this would work is you would set up the circuit, send data, then you would tear down the circuit, right? And which means anytime the circuit is idle, it cannot be used by anyone else, right? So the question is, are the links permanent? So yeah, as I said, these circuits are sort of established for a while, and then they need to be explicitly toned down, right? Now, the underlying technology whereby you would do this splitting up, there were two options. There are two options really. So one is to do what's referred to as FDM, which we've already seen when we looked at ADSL and cable. The idea being you split up the frequency bands into sort of pieces, and then you allocate one piece to each circuit. So a very naive example of this would be, say, we have got 4 users, each requesting for a circuit. You would split up the capacity into 4 channels and then allocate one channel to each user. So effectively, each user will transmit for the entire time, but just over a smaller band than the entire capacity of the channel. The other way to do this is, rather than split up frequencies, you split up time. So essentially you allocate specific times for each user, and then you create a sort of repetitive pattern, right? So each user gets to transmit over the entire frequency band, but just for a short amount of time. Now, effectively, over a large period of time, each user is going to get the same data rate. It just, here it's split up according to frequencies, here it's split up according to time. So the actual data rate each user would get would still be the same, right? It's just slightly varying in how this could be done. Now, again, these pictures are going to be, you'll see a lot of these kind of pictures. As I said earlier, these are what are referred to as timing diagrams, right? So the way circuit switching would work is where you would first set up the circuit. So you would send up what could be referred to as a control message requesting for the circuit to be set up. This switch would then check if it can actually establish a circuit, because the capacity might already be used. So it first needs to check that. Assuming it can, it will forward the request to the next switch, and so on and so forth. And then a final acknowledgement will go back all the way. And at this point, the circuit is established, and then the data can actually be sent right through. Now remember here, once you've set up the circuit, you're guaranteed to have reserved the resources, right? So assuming you're sending at the correct data rate, you can effectively just start sending all the data, and that will just pass through the entire circuit. And then once you're done, you tear down the circuit, right? So that's how circuit switching sort of works as a whole. Now, hopefully the problems with this are already apparent to you. Firstly, as I hinted earlier, the communication patterns are very bursty, right? So as I already said, when you're viewing web pages, there may be some delays in terms of the user actually reading the content and requesting. So you're kind of, if you set up circuits for downloading web pages like that, you'll be wasting a lot of bandwidth because no one else can actually use that capacity. It's not very, and I mean, think of doing this for hundreds or thousands or millions of users on the internet. It just wouldn't scale. It just doesn't make sense, right? So it's very inefficient and unscalable. The other issue is what data rate are you going to reserve? Because when you're browsing, the actual data rate you need is very low, say compared to when you're streaming a video, or like right now when you're actually watching this lecture live, right? So reserving a fixed data rate is very hard to begin with. So that's another issue. And the third issue is the poor switches along the way are going to have to do a lot of work, because they're going to have to remember each and every circuit that's established, right? So they're going to have to keep state about that. Each time a new circuit request comes, they have to check if that request can be accommodated. So it just creates a lot of work on these switches, and it's just not scalable, right? So luckily this technology lost, and we are not using this in the internet because it just wouldn't make sense to do this on a global scale, right? So hopefully that is clear. If not, please certainly ask me questions in the chat. But we'll move on to packet switching. Okay, I might just wait for a few seconds if there are questions here. Okay, if not, let's now start looking at packet switching, which is what is actually used on the internet. So this is much simpler, as you'll already realize. The idea is fairly straightforward. The app sending end takes the application message, it breaks it up into smaller chunks of formatted data. These are referred to as packets. Now, each packet will actually contain some control information, which is often referred to as the header, and then the actual data, which is referred to as the payload. So kind of like that. The header will contain a lot of information that's necessary to send the packet through the maze of routers till they, say, a maze of switches till they reach the endpoint. So one field in here, which probably is kind of obvious, is the IP address or the internet address, right? Because if you're sending something, you need to tell the network where it's being sent to. So that's one part of it. Another field could potentially be the age, because you don't want these packets to, if they are incorrectly forwarded, you don't just want them to keep looping in the network forever. So there's what's referred to as a time to live field. There's what's referred to as a checksum to protect the header, to detect errors, and so on and so forth. We'll again revisit all of this in a lot more detail later in this course. I'm just sort of giving you a quick peek into this, right? So the way this would work is you would say, if you're sending an image, this would be packetized. Essentially, part of the data gets sent in one packet. You add certain header fields, you send it out, and you keep doing that till you've sent out the entire image. So the header essentially could be thought of as an API. So you're including some extra information in there, which will allow the network to handle the packet. And then each switch will examine those header fields and then forward those packets towards the destination, right? So a quick peek ahead. Again, we'll revisit this a lot more. We'll come back to this slide a little later in this course, but effectively what's happening is that header field, the IP address effectively. Now, a real IP address is 32 bits long. Here, I'm just abstracting that over and just showing you 4 bits, but essentially there's an address. When a packet arrives at a router, there's something called a forwarding table that the router looks. So it's essentially doing a quick lookup to see where this packet should be sent to. So here you'll notice it gets a match 0111, which matches this third entry, which tells it should be sent out on the output link number 2, right? So this action is referred to as forwarding. And the core routers are just forwarding packets at a very high speed. That's all they're doing. They're just forwarding packets, examining this table, forwarding the packet. Now, the actual forwarding table itself is built using what's referred to as routing algorithms. So this is a global activity. It's essentially multiple routers participate in this process. They exchange certain control information to figure out what is the best path from, say, a source to a destination, right? So there are these routing algorithms that are running concurrently, which allow these routers to learn the sort of best paths from source nodes to destination. And based on that, they populate these forwarding tables. Right? Again, we'll revisit this in a lot more detail, right? I just wanted to give you a very quick peek of what's actually happening. Now, going back to the timing diagram that we earlier saw, so the one for packet switching would look something like this. So the green part here refers to the header. The gray part refers to the payload. So this packet is actually being pushed out, being transmitted out onto the link. So there's some delay to do that, essentially, to push the packet out. The packet reaches the switch. The switch does that forwarding lookup you saw in the previous slide. Now, in this picture, I haven't shown you all the outgoing links of the switch, but clearly a switch has many outgoing links. let's just say in this case, the packet is being sent out on this link. So then this packet switch pushes the packet out on this second link. Now you may ask, okay, what about the time to process the packet? Now, typically these packet switches are processing packets at the rate of milliseconds, even nanoseconds. So we kind of, unless explicitly told, we kind of assume the processing delay is minimal. It's not really accounted for unless specifically told, right? So this is how the timing diagram would look like. And remember, this is just one packet, right? This switch might be sending multiple packets. So for example, a second packet might be sent immediately after. So let me just draw it here. Just so I'm illustrating that. Right, so imagine a second. Oops, my drawing is a bit poor. Hopefully you get the idea, right? So this is packet 1. This is packet 2. That's the header part. And then this switch, imagine it sent out this second packet, right? So that would be. So these packets are sort of sent back to back, and then the switch is also forwarding them back to back, right? I'll show you another picture later like this with a bit more better drawing, essentially, right? What is the green bar again? So that's essentially just the header, right? So remember, each packet has certain header. And yes, it does create some overheads. We'll look at that specifically later, Tim, but yeah, that is certainly something we need to be aware of, right? That each packet being sent, you are including some extra headers. So there is certain overhead involved there, right? So we do need to be mindful of that. We can't just have arbitrarily large headers, right? And yes, the time would be based on the size of the packet and the transmission rate or the bandwidth, right? So we'll come back to this discussion of delays in the second lecture this week, where I'll talk about the transmission delays and all that. Right? Now you might wonder, could the switch actually start processing, start transmitting the packet as soon as it receives the header, right? So if you think about it, this is the process shown here is what's referred to as store and forward. So the switch receives a packet, stores it, and then forwards it, right? It may be possible to actually do this essentially. So as soon as the switch receives the header, it can examine the header and it now knows where to send the packet. So as the rest of the payload is coming in, the switch can sort of start sending the packet. So as bits come in, it can start trickling out those bits. So this is what's referred to as a cut through switch. Now, there are certain, of course, there's an advantage here in that the delay is reduced, but there are certain drawbacks which we'll perhaps visit a little later. So for now, we'll skip over this point, and we'll, for the rest of this discussion, and until explicitly told, we'll always assume that packet switches do store and forward. So they receive a packet. Once they have the packet, they figure out where it should go to, and then they send it forward. So this is what's referred to as store and forward switching. Right? Now, one thing to remember is the packets are actually independent. Now, typically, again, when you're sending back-to-back packets, typically all of them would take the same path towards the destination, but there's no guarantee, right? Now, you might wonder why. Well, remember here we talked of this forwarding table and how this forwarding table is populated by the routing algorithms. So it may so happen that, let's say we are sending 100 packets, right? So imagine 10 packets were sent along this route. Now it may so happen that based on certain network conditions, the routing algorithms actually make a change in the forwarding table while we are sending those stream of packets, and say the outgoing link may actually change for various reasons, for certain changes in the network topology, right? So some of the packets may go this way, the remaining packets may go this way, right? So there's no guarantee that when you're sending back-to-back packets that all of them will necessarily take the same route, because each packet is treated independently, right? Each packet has its own header, So the router is not sort of keeping state and saying, oh, the previous packet was sent this way, so the next packet should also be sent this way. No, it doesn't do that. For each packet, it will do that lookup independently, right? Because there's no notion of a circuit, there's no notion of any state. Each packet is actually treated independently. Right? Another thing to remember is the resources are not being reserved here, right? So we are not making any explicit reservations. The packet simply make use of the available bandwidth, right? So this is what's referred to as statistical multiplexing. So before we get to that, a question, how is the header determined? So the header is determined by the source. So we'll look at that a little later, but it's essentially the source that's creating the information in the header, right? Does store and forward allow a switch to verify the validity of a packet before forwarding via checksum in the header? Yes, typically that's what packet switches would do. And in fact, I think I did include that here, right? Somewhere I said, yeah. So typically the header will include certain information that will allow the switch to check if there are errors in the packet, because there's no point forwarding a packet if it has errors, right? So we'll again revisit checksums a little later in this course. Right. Okay, yeah, so packet switches, they leverage this concept of statistical multiplexing. Now, actually, I've run out of time. So let me do the following. Let's pause here and we'll restart exactly at this point when we meet. I do have one important announcement to make. I'll also be sending this out through the website. Now, unfortunately, I'm double booked for this Wednesday. I had already agreed to serve on a panel for some blockchain Australia that they're organizing a panel which they invited me for, and that's exactly clashing with our lecture on Wednesday, unfortunately. That's just a one-off. From next week, of course, we'll be having lectures on Monday and Wednesday as advertised. But what I'm going to do is I'm actually going to record the Wednesday lecture tomorrow. And in fact, I'm happy to do that live. So I'm happy to just send you all the Zoom link for that, which I'll do through an announcement later. And if you want to, you can join that lecture live. If not, you can always watch it through YouTube or Echo 360, right? So look for an announcement later this afternoon about that. I'll set up the link for tomorrow. I think I'll do it at 9:30 a.m. Australia time, 9:30 to 11:30. So if you're free, certainly join live. If not, just watch it offline. But we'll go back to the normal Monday, Wednesday slots starting next week. Really sorry, I already committed to them and I don't want to back off. So I'll see you all tomorrow and have a wonderful rest of the day and a good start to your week. Bye-bye. And yeah, if there are any questions, just post on the forum. Bye, everyone.